Hello, my name is Daniel and this is my presentation for Lab 4. Introduction. So our purpose is to use physics and circuits principles to analyze various circuits, their behaviors, and the relationship between voltage and time of a capacitor, to later find the time constant using an online circuit simulator. The key principles are Ohm's law, Kirchhoff's loop rule, node rule, and the RC time constant formula, and all of them are shown to the right, their exact formulas. Some assumptions we had to make: the resistance when using a voltmeter and ammeter, we had to neglect that, and then no external fields or confounding variables could be accounted for. We had to ignore those as well. And our main result is that our RC time constant was 5.9, close to 6 seconds. Experiment part 1. So this is the first part of the experiment. We created a circuit as shown to the right with 2 ammeters, 2 batteries with 1.5 volts each, and a 47 ohm resistor and a 100 ohm resistor. And you can see those to the right again. Initial conditions: no resistance, the system's the circuit, and the surroundings is everything else. And then we predicted the current would be 0.02 amps using Ohm's law. We divided the total voltage by the total resistance, and then the actual reading, as you can see by the picture, is 0.02 amps. And then if you reverse the connections, it's negative 0.02 amps. So same magnitude, different direction. And then for the second part, we replaced an ammeter with a voltmeter, and then the reading on the voltmeter was 3 volts, same as the batteries, and then the ammeter read 0 amps, and this is because the voltmeter just reads the voltage/potential difference across the gap. It doesn't close the circuit enough for the current to flow, so the circuit is still open, and the current is 0 amperes as seen by the ammeter. And then continuing, we then closed the circuit with a wire, only had 1 ammeter, and then we used the voltmeter to see the potential difference in different locations across the circuit, and you can see the diagram to the right. And then at AB it was 3 volts, BC it was 0 volts, CD was negative 0.96 volts, DE is 0, EF was negative 2.04 volts, and FG was 0, HG was 0, HA was 0. Using the loop rule, we can see that all of these summed out to be 0, which is what the loop rule is supposed to turn out. So we did this correctly, and then the current remained 0.02 amps. And this is just a graph showing how the current drops, the voltage drops across every resistor, and as you can see, that's why our values earlier were negative, and you can see across each of the resistors they drop until it becomes 0. Observation: so why doesn't the ammeter reading change when you add a voltmeter to the circuit? Well, that's because a voltmeter is designed to affect the circuit as little as possible. So technically a small current flows through it, but it's negligible in our instance. And if we place the voltmeter across a 100 ohm resistor, what is the ammeter reading? Ammeter reading remains 0.02 amps. And then if we place an ammeter in parallel to a 100 ohm resistor, the current increases to 0.06 because it can bypass the resistor with a new path. And then the resistance of elements across the circuit, using Ohm's law, it turned out to be the resistance across the 47 ohm resistor is actually 48 ohms in magnitude. For the 100 ohm resistor is 102 in magnitude. And for the wire and the ammeter, they're both 0 ohms. So really close to the actual values we found earlier. Now part 2 of the entire experiment. So there's a new circuit. We connected a 100 ohm light bulb, 9 volt battery, and 200 microfarad capacitor in series. And then when discharged or disconnected, the battery light is when discharging or disconnecting the battery, the light is bright, but eventually dims as the current goes to 0. And whenever the capacitor is charged and discharged, the current goes to 0 as it finishes charging and discharging. Then time to charge a capacitor with a 10 ohm bulb is 7.38 seconds. Time to discharge 7.78 seconds. Time to charge with a 20 ohm light bulb is 14.68 seconds, and to discharge is 15.12 seconds. And then here we use the logarithmic linear relationship of voltage across time using a 30 ohm bulb this time, and we use that logarithmic relationship to get a negative sloping curve, linearly sloping, and then the slope divided from -1, so the inverse of the slope is essentially our RC constant, which is 5.9 seconds. The expected RC constant is 6 seconds using the resistance times the capacitance, which is 6 seconds, so it's pretty close as well. And then conclusion: what if the overall current would have, or what if we were doing this in real life and used an actual ammeter? And what would be different, how it would have affected the circuits? The overall current would have decreased because real ammeters have resistance. Then what if we were doing this in real life with a real battery to charge a real capacitor and no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? So with this model, the capacitor would charge virtually instantly. In real life, it would take time because there's resistance, so this prediction would not happen in real life. And then possible error, we could have set up the circuit wrong, the online simulator could have glitched, or we could have neglected resistance. We shouldn't have, so yeah, y'all have